Okay, so in question number 2, you can see here we've got an integral, definite integral we've got to calculate here. So 0 to 1 of 2x plus 1 over x squared plus 1. All right, so first of all, first thing we need to do to make life a little bit easier for ourselves is we need to actually split that into 2 bits. So up on the numerator we've got 2x plus 1, so we're going to split it into 2. So we'd go 0 to 1 of the 2x over x squared plus 1 dx plus the integral of 0 to 1 of 1 over x squared plus 1 dx. All right, and now we're going to go from there. All right, so the first one here is a couple of different approaches that you could do. But when you look at what's on the bottom here, x squared plus 1, if you were to differentiate that, you would in fact get 2x. So the way I'm going to do it is I'm going to say let u equal x squared plus 1 on that first bit. All right, and so this is just this first integral here, not the second one. The second one I'm actually going to leave it as it is, and we'll get to that in a minute. So du dx is 2x. All right, so if we do a rearrangement, du is 2x times dx, and because I've changed from a variable of to u, I need to actually change these limits. All right, so when I do that, so if x is equal to 0, using x squared plus 1, my u would be 0 squared plus 1, which of course is 1. And for the upper limit, when x is equal to 1, my u would be 1 squared plus 1, which of course is 2. So this first integral is the same as, so the 0 to 1, 2x x squared plus 1 dx, it's the same as 1 to 2 of 1 on u du. All right, and so then when I anti-differentiate that, that's log to the base e of u (1 to 2), and so that's log to the base e of 2 minus log to the base e of 1. Now log of 1 is of course 0, so this bit here then is simply log to the base e of 2. All right, so if I then go back and say, okay, that's this first bit. So I'm going back and I'm going, all right then, so the first bit that I had, so the 0 to 1, 2x x squared plus 1 dx, that is log to the base e of 2. The other part is 0 to 1 of 1 on x squared plus, whoops, that's not right, the plus 1's not there, the plus 1 is here, dx. Now if you go and you have a look at your formula sheet on this one, you should see the arctan, or the inverse tan minus 1, and you'll see then that this here, in fact, is tan minus 1 of x between 0 and 1. All right, so that's on the formula sheet, which I should have brought up, but I haven't brought that up to flick over and show you, so you just have to take my word for it. All right, so this first one, log to the base e of 2 plus, okay, so what have we got? We've got tan minus 1 of 1 minus tan minus 1 of 0. The log to the base e of 2 is still there. Inverse tan of 1, so it's pi on 4 that has a tan of 1. Some number that has a tan of 0, well, that is 0, the angle I should say, not the number. And so our final answer is log to the base e of 2 plus pi on 4. All right, so that's one way of approaching it. So I've used this substitution. I've substituted here to do this first one. You can shortcut that. All right, but I've chosen not to. And so, yep, that's about it. Just if you do the substitution, just be careful. All right, because one of the things with the substitution letting u equal that people forget to do is change these limits. All right, because we're in terms of x. And once you go and you change for that substitution of u, you need to change the limits to be what u is equal to when x is those particular values. And that relates, of course, to what substitution you have made. All right, I better stop there, otherwise I'll end up waffling along too much.